All right, so I think we're ready to get started. I'm kind of a giving the last minute introduction here for Brian, since he's a Blue Waters user, been on the system for quite a while. So Brian's here. He's been here since, I guess, Tuesday, actually. Been here for a while. So, but you're familiar with the campus. So first, I'd like to note out that Brian was actually an undergrad here from 97 to 2000. He was a physics engineering student. Engineering physics student, sorry. So I know there's some people in the audience who might have been here during that time, so you could have overlapped with Brian. And he got his PhD in physics from the U of I, although I guess technically you were not physically present at the U of I.
For very little of it.
2006, you were in San Diego at that point. And then, is that when Mike Norman moved to San Diego?
That is why I moved to San Diego.
So people who know Mike Norman know that he took a lot of people with him. And then from that point on, you moved apparently to Los Alamos, did a postdoc there. And then at some point, decided to move on to academia, and you ended up at Michigan State University, where you are now.
That's right.
And then you mentioned you're doing a sabbatical at University of Michigan.
That's right.
And I don't know enough to make any Big Ten jokes, so I'm not too sure.
Keep it to yourself.
And we bailed out yesterday, so I guess it's not a big deal. So Brian's here to talk about some of the work that he's been doing on Blue Waters, and he's been one of our more productive Blue Waters partners, I guess. In Blue Waters, we call people partners and not users, but I'm old school, so I still say user. Mm-hmm. Anyway, so Brian's been doing a lot. He's produced a lot of data. We can say that he's one of the top project occupiers on the nearline storage system, so that's pretty good. Just about a petabyte of data. So he's obviously done a lot of running, a lot of work, and he's got a lot of interesting science. We saw some of it yesterday in a brief conversation with Brian. So Brian's going to tell us a bit about what it takes to do a modeling of the universe. In a box, I guess, periodic box maybe, I don't know.
Right, of course.
Anyway, so and I'm supposed to note that we do have our small reception after the colloquium is over, so thanks, Brian.
Thank you very much. Can everybody hear me? Is the audio level reasonable? Fantastic, I see various thumbs up. Right, so it's really a pleasure to be here to talk about the work that we're doing on Blue Waters. As Greg said, I'm an Illini. I got all of my degrees from here, and it's really nice to come back to campus and be baffled by all the new buildings and things. But it's been fun. We've done some really wonderful things. And so what I'm going to do today is tell you about our efforts to study the earliest generations of galaxies in the universe using Blue Waters. And galaxies are interesting and important because they're the building blocks of the universe. So understanding galaxies is the key to understanding properties of all sorts of interesting things like dark matter and dark energy. And also, galaxies are often very extreme and very complex physical systems. And so, but before I go on, I just want to mention I'm not doing this alone. In fact, I'm not the person who's done most of the work. I've been working on this PRAC project on Blue Waters with a variety of people that are listed down here in the left bottom right-hand corner. Mike Norman is my co-PI on our PRAC, and then Peng-Fei Chen, Britton Smith, John Wise, and Hao Xu are all folks who have put in a tremendous amount of effort running and analyzing the simulations. And Hao, in particular, I think is responsible single-handedly for 100 million core hours and most of a petabyte of data, just all on his own. And so, but also, working on Blue Waters and getting started with the early system, early user time, and getting going on the machine was was a lot of effort on lots of people's parts. And so I just wanted to thank, all the folks here at NCSA, the Blue Waters team, Mana Shigajbe, who's my technical point of contact, and Greg and Bill Kramer, and various other folks. I'm not going to go through the list again. But thank you very much, because it really, this whole thing has been a tremendous group effort, and we could not have done the awesome science we're in the middle of doing if it weren't for lots of contributions from lots of different people. So, okay. So first off, what are the big questions in galaxy formation, or at least the ones that I'm trying to answer? So the universe is 13.7 billion years old. Galaxies have been around for essentially that entire time, except for a very brief, less than 1% of the time at the beginning of the universe. And we have lots of questions. We want to know how the first stars and the first galaxies look like, how they look like, how they behave, how galaxies like our own Milky Way form and how they evolve, And with galaxies, they interact very heavily with their environment, and we want to understand how these galaxies interact with their environment. And these are all sort of big questions relating to galaxies and how they evolve. And the work that we're talking about today directly addresses basically all of this. But I appreciate this is not an astrophysics seminar, so I want to set the stage for what I'm talking about and actually talk about galaxy evolution and cosmological structure. So what do I mean when I say cosmological structure? So here's the big picture. This is from something called the Sloan Digital Sky Survey, which is an astronomical survey that's been going on for about 15 years in total now. And what you're looking at is a map of the galaxies in a very thin slice, right? So imagine a tiny, tiny little wedge out into the distance. And starting, you can sort of figure out pretty easily where the center is. The Earth is right there. And we're going about 2 billion, or 2 gigalight years, so 2 billion light years out into the distance. And so each one of the points on here is a galaxy. They're colored by their galaxy type, but this is what we're talking about when we're talking about cosmological structure. And some of the important things that you see, there's sort of a web-like nature to it, and you get these big filaments and clumps and things like that, because that's what gravity does. As the universe expands, gravity pulls stuff together, and it tends to make things that look like sheets and filaments and clumps. And so at all scales, in the universe, when you're looking at astrophysical structure and cosmological structure, you see these repeated patterns of sheets, filaments, and clumps because gravity breaks things up that way. And also, there's a huge variation. You know, some of these regions are really dense and full of galaxies. Some of these other parts are completely empty and they're voids and there's almost nothing there. So this is the big picture of what I'm talking about with cosmological structure. But let's zoom in a little further. So here's a picture of something called a galaxy cluster. I think you can get the hint about why it's called a cluster of galaxies. Every point on this, everything you're looking at on this image, with a couple of exceptions, is a galaxy. That happens to be a star, and that happens to be a star. But pretty much everything else is a galaxy. And so this is Abell 1689, which is about 2 billion light years away, and it's one of the largest galaxy clusters known. It weighs about 2,000 times as much as our own Milky Way galaxy. And these are like the largest gravitationally bound structures around. And they're actually so gravitationally, they have such strong gravitational fields that they actually cause light to bend around them. So in the way that light would bend, would be refracted in a magnifying glass or something like that, you also have sort of an analogous effect with gravity. So the light from background things gets bent around these galaxy clusters, and so you see these pretty little arcs, like, oh, forget it, I'll just use this. You see these sort of pretty little arcs, which are lensed and magnified images from background galaxies. So this is another aspect of cosmological structure. Here's something that's maybe a little bit more familiar. You might note it from the default Mac background. This is the Andromeda Galaxy. It's a spiral galaxy. It's only 2.5 million light years away. It's very similar to the Milky Way, the galaxy we live in lots of ways. It weighs almost exactly the same amount. It's the same age. It has lots of similarities. But it's full of gas. It's forming stars like crazy. It's also going to, it's coming right at us, and it's going to merge with the Milky Way in a couple billion years. So we got to watch out for that. Not anytime soon, of course. But this is an example of what we call a spiral galaxy. So very much like our own Milky Way. And you can, if you look hard, you can see the spiral density waves and the dust lanes and things like that in there. But then here's an example of a completely different kind of galaxy. So sometimes I like to have people try to point out where the actual galaxy is. The room's too big and there's too many of you, so I'll just show you. It's this little tiny smudge of light here. All of the actual points you can see are foreground galaxies. This is a dwarf galaxy. It's outside of the Milky Way, so we have to look through the Milky Way to see it. So all the points are stars that are actually in our own Milky Way. They're annoying foregrounds for us. But this is a dwarf galaxy that's a part of the local group of galaxies. It's a satellite of Andromeda, that one that I just showed you. It's really, really dim. It's very hard to see. It's actually 10,000 times smaller than our own Milky Way. and there's very little gas in it. It's not forming stars at all. So it's a very different kind of galaxy than the Milky Way or Andromeda. And then finally, here's, I think, my favorite picture in astronomy. This is something called the Hubble Ultra Deep Field. And it is a very tiny field of view. So they took the Hubble Space Telescope and spent 2 weeks looking at this very tiny, very dark patch of sky where, in surveys there's nothing in it. Until you look really, really deeply, you see nothing. And so the field of view was 1/10 of the diameter of the full moon, as you see it from Earth. So if you hold like a tiny little 1 millimeter squared piece of paper at arm's length, that's about the size of this Hubble Deep Field. And it's the deepest image of the universe that was ever taken in visible light up to this point. And so every point in here, except for maybe 2 of them, are galaxies. And what you're doing is light travels at a constant rate, and the further you look back, the further things are that you're looking at, the further back you are seeing them in time. Because if all the light is getting to you at a constant time, if it's really close, the light left it recently. If it's 10 billion light years away, the light left it about 10 billion years ago, approximately, and so on and so forth. And so in some sense, this Hubble Ultra Deep Field is a time machine for those of us that are doing galaxy formation, because it lets us look back in time more than 13 billion years to only 5 or 10% of the age of the universe, so within several hundred million years after the Big Bang. And so we can learn everything there is to know about galaxy formation from this one image. And that's only just a tiny little bit of hyperbole. It's really incredibly informative. And there's 10,000 galaxies in here. And so one of the things that you can see is essentially the bigger stuff is closer. And you can see that a lot of these big galaxies, like this one down here in the bottom right-hand corner, are these pretty spiral galaxies. You see some other things that are kind of little red blobs. Those are what are called elliptical galaxies. They're around the same size as the spirals, but they don't have any dust, or they don't have any gas, and they're not really forming any stars. But you see lots and lots of those all over the place. And that's a very common thing to see among big galaxies in the present day universe. Lots of spirals, lots of ellipticals. They look very symmetric, they look very pretty. But then when you start looking at stuff that's further back in time, it looks like this. These are galaxies that kind of look like train wrecks. They're all forming stars like crazy. They have different colors. They're generally, some of the bluer ones tend to be forming more stars right now. They all have lots and lots of gas, as opposed to those elliptical galaxies or that dwarf galaxy I showed you. And they tend to be forming stars like crazy. So as we look back in time, we see that. But none of them really look like the Milky Way or an elliptical galaxy. And when we go even further back in time, so these are the dimmest and most distant galaxies in this Hubble Ultra Deep Field, they all look very red because the expanding universe takes all of the visible light and ultraviolet light and shifts it towards infrared. So everything looks redder the further it gets away from us. All of these things, as far as we can tell, are even more train wrecky. They have lots of gas, they're forming stars like crazy, they seem like they're always merging, they're always doing things all the time, but they look very, very different than the galaxies you see in the present day. And so we see this trend of, over time, galaxies get bigger, they get more regular, they look more like spirals, they look more like ellipticals, they change a lot. And the general theory behind all of this is what we call hierarchical structure formation. And this is backed up by tons of different kinds of evidence. The general idea is that you have small galaxies that form early on, and they merge together to form ever larger galaxies. And so galaxies like the Milky Way or Andromeda are actually the product of many, many generations of galaxies merging together. And I have a movie that I'm confident many of you have seen before that was done by the Advanced Visualization Lab. And this does a great job of showing how galaxies are built from a simulation that I did, I think, almost 10 years ago now, but it's such a beautiful rendering. And what you're seeing is galaxies. The galaxies are forming hierarchically. Little galaxies merge with each other to make ever larger galaxies. The process of merging takes a lot of time. We're looking at billions and billions of years of evolution here. But you have sort of successive mergers. Galaxies get consumed by the bigger galaxy, and it just keeps on going, and you end up with this sort of thing, which, well, you know, in our more modern galaxies, our more modern simulations, they look an awful lot like the Milky Way or Andromeda. In this simulation, it's not quite as realistic looking, but it captures the spirit of the thing. Okay, so that's how galaxy formation, that's the big picture of galaxy formation and cosmological structure. And so, of course, when we want to run something on blue waters and we want the NSF and the University of Illinois to trust us with all this computer time, we have to explain why this is interesting. And so, you know, a lot of people find galaxies fundamentally interesting. Astronomy's fun. But like I was saying right at the beginning of my talk, galaxies are the building blocks of the universe. So if you want to understand galaxies, you need to understand galaxies to be able to understand the structure of the universe. And if you want to probe dark matter, what is dark matter? What is dark energy? Does dark energy change its properties over time? You really need to understand the galaxies, because the galaxies are how you detect the presence of dark matter and dark energy and learn things about them. Also, galaxies are very complicated physical systems, and we'll get into the complexity in a little bit, but they're very interesting from a physical point of view. You can learn a tremendous amount about stars and magnetic fields and all sorts of good stuff by studying galaxies. And also, of course, if you want to be philosophical, it answers the questions of, you know, how did we get here and where are we going and all that. So, you know, also they're just really neat. You know, they're fun to simulate, so that's honestly what motivates me. Anyway, so then there's the big question of why is this challenging? Why is this a problem that is worthy of doing on a supercomputer like Blue Waters? And there's essentially three reasons. Galaxies are complex. Galaxies have a huge dynamical range, and then there's also an issue of sample. You need lots of galaxies. So let's go through those one at a time. So let's talk about complexity. So what are the physics you need? And by the way, pardon the laundry list I'm about to give you, but I want to give you a flavor for the physics that's required. And all of the physics that I'm going to show you, the pieces of physics interact with each other, often in very nonlinear ways. So, okay, so the first thing you need to understand is cosmology. The universe is expanding. You have to have a model for how the universe expands and how it affects the structure that's forming within it. Gravity drives everything in astrophysics. The pull of stuff, the mutual pull of objects in the universe is the engine that drives absolutely everything. It's what makes clouds of gas collapse. It's what turns on fusion in stars. It's what drives the formation of black holes. And it's what drives, you know, the jets, the big active galactic nuclei, the jets that come from black holes. It's absolutely critical to model that. You have to model hydrodynamics. Most of the baryons in the universe, the actual stuff that you and I are made out of, is a plasma. It's hot, it's very diffuse. You have to model the equations of hydrodynamics. And these are the things that you need to understand sort of at minimum to claim that you are doing cosmology, that you're trying to understand galaxy formation. But really, there's more. This gas that I was talking about is heated in a variety of ways, by radiation, by compression. It also cools. It cools off due to microphysical processes that, you know, you actually would learn a little bit about in your chemistry classes. There's also these things called stars that form, and they don't just form. They tend to shine very brightly with lots of radiation, and the bigger ones also tend to explode. So you need to model that process of stars forming and evolving and exploding. And you also need to model how, say, black holes form and how they feed back into their environment. And then finally, if you're working at what's the cutting edge of structure formation now, modeling structure formation, you have to worry about things like radiation transport. That's to say, all of those stars that I was talking about produce lots and lots of radiation. Radiation is an easy way for those stars to reach out and touch something that's further away, pretty far away. So you have to model that, and that's both complicated and very, very expensive. You also have to model magnetic fields in a lot of cases, because magnetic fields are extremely important when you have a plasma, and so that can be a challenge. And then we put et cetera, and within et cetera you have things like thermal conduction in a plasma, cosmic rays. I'm sure if I sat here and thought of a big laundry list, I could come up with some more examples. But the point is, there's a lot of different physics that's going on all at once. And it acts on different time scales, and it acts on different spatial scales. And all of these things interact with each other. The expanding of the universe, the cosmology, affects gravity. The pull, gravitational pull, interacts with hydrodynamics. Gas pushes back when you try to compress it. But the gas can be heated and cooled, which affects its hydrodynamics, and so on and so forth. So there's a lot of complexity in that. But then there's also this issue of dynamic range. And what do I mean by that? Well, we can't just simulate a galaxy. We have to, a galaxy interacts with neighboring galaxies, it interacts with the cosmological filaments that it's forming in, and you need to have a big enough volume of the universe to get the kinds of galaxies that you're interested in studying. So if I was interested in the Milky Way, I would have to decide what's the size of a fair sample of the universe. And that's something like, I put this in orders of magnitude to make it easier to just do the division, but a fair sample of the universe is maybe 100 million light years across. And that's not that big in cosmological terms. It's just big enough to get a handful of Milky Way type galaxies. The actual size of the Milky Way and all of its satellites and the group of galaxies that it's in is about 1 million light years across, which still sounds inconceivably large, but it's a factor of 100 smaller, so we have to get at least that scale. But, oh wait, galaxies are composed of stars, and we need to understand where the stars form and how they feed back. So the size of the star-forming cloud is more like 100 light years across, which is really small compared to that fair sample of the universe. And that gives you about a factor of 1 million in spatial dynamic range. So we have to be able to sample, or we have to be able to simulate both this fair sample of the universe that's 100 million light years across, and also be able to say there's a star-forming cloud there, and it's making stars, and those stars are exploding. And so that gives us a factor of 1 million. And then on the time side, we have similar problems. The age of the universe is, well, in round numbers, 10 to the 10 years, 10 billion years. It's actually 13.7 something billion years. And then the dynamical time, sort of the relevant time scale for these star-forming regions, is actually about 10,000 years. And that gives us a factor of 10 to the 6 in time, as well as a factor of 10 to the 6 in space. So in other words, if I want to model how the universe forms, I need to go through a factor of 1 million in spatial scale, as all of my galaxy collapses and forms stars, and I have to take on the order of 1 million time steps to do it. Starting to get the sense that this might be a real pain in the rear end, right? Technical challenge. And then there's another problem, and that's the issue of statistics and sampling. And this is a picture of Memorial Stadium. When I was an undergrad here, I watched the Illini get beaten many, many times there. Things got better after I left. But it's Memorial Stadium. According to Wikipedia, it holds 60,670 people. But I'm showing you this picture because it's actually sort of analogous to what astronomers have to deal with when we study galaxies. Galaxies evolve very slowly, and we get snapshots of them. So imagine on a Saturday you go to an Illini game, and as people are filing into or out of the stadium, you take all their pictures. And then you give somebody a thumb drive with the pictures of all the folks that walked into the stadium and said, okay, from this thumb drive full of pictures of people, tell me about humans. Tell me how humans grow, how they're born, how they grow, how they live their lives, how they evolve as a being, and then how they die from this stack of pictures. And that's basically what you're doing with astronomy. You're trying to figure out from a stack of pictures how galaxies evolve over time. And so there's a statistics issue. You need lots of those pictures to start to puzzle this together. But then there's also a sampling issue, because let's think about a football game. Does everybody that has a baby bring them to a football game? Yeah, no, you'd be nuts. I have a 2-year-old. That's the worst idea, right? And also, perhaps, maybe you wouldn't bring your great-grandmother to a football game. Mine happens to be a big Illini fan, but most, no, right? And so you're getting a biased sample of people, right? It's not as if we just sort of went to the mall and netted the first 100 people that walked by. It's not, we're seeing the people who are going to go to a football game. So in galaxies, when we're talking about galaxies, we see the galaxies that are shining brightly. We don't see small galaxies or dim galaxies, the ones that are tiny and just forming, or the ones that are very old and composed of old dim stars. And so it's not the entire population. We see the ones that are easy to see. And so together, needing to have lots of galaxies to simulate, needing to observe lots of galaxies and knowing we have a biased sample presents us with a challenge. That means that if we want to study galaxy formation, to really trust our models, we have to compare large populations of simulated galaxies with large populations of observed galaxies. So in addition to having one galaxy where I have a factor of 1 million in space and a factor of 1 million in time, really I want hundreds or thousands or millions of galaxies that I'm simulating with that resolution. And so, with that level of fidelity. And so, of course, the outcome of that is that you ask for a tremendous amount of time on blue waters. And so, it's really a problem that's worthy of a computer like Blue Waters because of both the physical complexity, the dynamical range, and the sampling issue. Sort of in all of those dimensions, it really demands a tremendous amount of both technical sophistication on the part of the programmer, but also just an awful lot of computational horsepower. Okay, so first off, in this particular project, the one I want to tell you about today, the one we've done on Blue Waters, what we're trying to do is understand the first generations of galaxy formation. So I told you about a laundry list of questions I'm interested in. This is essentially addressing the question of how do the first galaxies form, how do they evolve, and ultimately how do they turn into galaxies like the Milky Way that we're in. And the first galaxies are very important. In those first galaxies, you're setting the stage for the rest of structure formation, right? The universe is 13.7 billion years old. That first 500 million or billion years is critical because that's when you make the first stars. That's when you make the first black holes. The black holes that form go on to grow by many, many orders of magnitude. And you see at the center of every big galaxy in the universe today, a supermassive black hole that's millions or billions of times the mass of our sun. And somehow, those things grew from seeds that are 1 or 10 times the mass of our sun. But you see it in every single galaxy, so you know there's this connection. And they had to have formed very early on. We see them in galaxies all the way as we look all the way back through the Hubble Deep Field. And again, these first galaxies process the universe. They fill the universe with metals. They fill the universe with radiation. So really, it's setting the stage for everything that's going to happen in the 13 billion or so years that comes after that. So that's what we want to do, is understand those first generations of galaxy formation. So we set this quite a task for ourselves. Okay, so how do we do it? Well, we use the Enzo adaptive mesh refinement code. And so this is actually an NCSA original. The first version of Enzo was written by Greg Bryan, who was one of Mike Norman's grad students, who was sitting in a cubicle over in the Beckman Institute when he wrote Enzo. And since then, it has moved from his graduate project to something that a ton of people have worked on, including Matt Turk, who's over there, myself, probably about 24 other people. Tons of resources have been poured into this, and we like it so much, we're giving it away for free. You can go to enzoproject.org, and you can learn about, you can download it and install it and play with it. And maybe if you're nice and good, somebody will let you on Blue Waters with it. But, but it's an adaptive mesh code, and we'll talk about what adaptive mesh means. But it has lots of physics in it. It has dark matter dynamics and hydrodynamics and magnetic fields and radiation and all that good stuff. And so really, actually, here's what it does. It solves all this stuff. And so, yeah. So I'm showing you this because I don't know. I had it. So But this is the slide you show when you want to intimidate everybody or put everybody to sleep. But but the point is, Enzo is very sophisticated and does a lot of things. It, for those of you in the audience that think this way, you combine a bunch of different hyperbolic and elliptic differential equations on a structured adaptive mesh grid. Okay, nobody got that? Let's move on. So, but this adaptive mesh refinement part is very important to the whole endeavor because we have this issue with the universe is very, very big. Galaxies are much smaller than the universe. Stars are much smaller than galaxies. So we have this huge range that we need to deal with. So adaptive mesh refinement is a trick or a numerical technique for dealing with that. So let's imagine we have a simulation volume. Let's put something in it to make it interesting. So this is from one of the simulations that I did when I was a grad student forming the very first generation of stars in the universe. We've done much, much better than this since then. And so we want to simulate this. But all this stuff, we're looking at the baryon density, and all the stuff out here in blue is boring. Nothing's going on there. Who cares? I don't want to waste my CPU time on that. So on the other hand, this stuff here, where it's red and yellow, that's where the dense gas is. That's where the stars are forming. That's where all the good stuff is happening. So what I do is, I break up the universe into a bunch of little cells, and then in each cell, I use some algorithm to identify what's exciting and what's not exciting, what's worthy of further study, or worthy of being refined further. And so one way to think of this is, in here, I'm just calling it halos and voids. Nothing's happening in the voids. Everything's happening in the halos. So in these two boxes, stuff is happening. So what I'll do is I'll put down a grid that's more finely resolved. And this grid doesn't just go to smaller spatial scales, it takes smaller time steps, because in addition to not having a lot of stuff in the voids, things move slowly out there. There's not very much interesting happening. We can sort of take a big time step and not use a lot of computational time to model what's going on out in the voids because not much is happening. And so, and the way that gravity works, the closer things get, the faster they move. So when stuff collapses, when the galaxies start to form, everything starts moving faster in the galaxies, so we want to put more resolution there in time as well as in space. So that's what's going on. So in these smaller cells, we're making better spatial resolution and we're taking more time steps, so we're resolving it more finely. But there's still a lot of wasted space here. So what I can do is recursively say, well, some of this is interesting, let's resolve that. Okay, but again, I can keep doing this over and over and over again and just really resolve the heck out of the things that I'm interested in. And so that's where this idea of adaptive mesh refinement comes from. And in the simulations that I'll talk about today, some of them do this for many, many orders of magnitude, more than just a factor of 1,000,000, more like a factor of 10 billion. And I think Matt Turk actually might be the world record holder for the number of levels of adaptive mesh. And it was, what did we figure? It's 42, right? And that's roughly analogous to, what is it? It works out to 10 to the 12, is that right? So yeah, so basically going from the size of the Earth down to the size of a virus. So it's a lot, it's pretty cool. Okay, so this is sort of the pictorial representation. Let me actually show you a dynamic example because it's adaptive. It can change over time and structures move over time. So I'm gonna show you something called a Sadov blast. And so this is just it's an explosion. So it's going to go, which is what explosions do. So the field you're looking at is just the gas density in the explosion, and then you'll see the grid patches on top of it. And so this is what the adaptive mesh in Enzo is doing. As this blast wave moves outwards, this red stuff, that's the blast wave, we're refining really highly around where the blast wave is and refining very poorly everywhere else. And then we're refining on a slope so that, well, anyway, it doesn't matter. So, but the point is the refinement follows the interesting stuff. And we can just show you the grids, and you can see how the grids move outwards. And so the way that Enzo is built, it puts the grid patches, it tries to put the grid patches only where it needs them, where the user says, this is an important quantity to follow, you need to follow this thing, and puts it only there, because then we put all of our computational resources where we need it, and we don't waste it in places where we don't. And so, I'm talking about cosmology and galaxy formation, so let me just show you this as applied to a big simulation of structure formation. So this is a simulation of structure formation. Again, done with Enzo. You're looking at the matter over density. So really, it's just all the cosmic web where all the cosmic structure is. And so this is a much more complicated structure than that Sadov blast that I just showed you. So what does the adaptive mesh look like evolving over that same period of time? Okay, so there's 3 levels of grid refinement, and you'll see how they build up over time. And so this is projecting through the entire volume, so it looks like there's lots of grids. And there are lots of grids because it's a pretty big simulation, but really only a very tiny volume of the universe is refined to high level. And the reason that we can do that is stuff collapses in the universe. So where you need to have the good resolution and where you need to take lots and lots of time steps is only a tiny, tiny part of the volume of the universe. And so in that way, these adaptive mesh type techniques are really useful for concentrating the power, the computational power, where you need them. Because if we wanted to simulate this whole thing on just sort of a fixed grid where everything's very regular, that would make my life much easier as a programmer, but you would not be able to do this on any computer for the foreseeable future. So, so this technique lets us do all this stuff. Okay, and then I would be remiss if I didn't mention that the thing that we use for doing all of our analysis and all of our visualization is something called YT. It's been absolutely crucial to the success of this project, and it's developed here at NCSA. So Matt started working on it when he was a graduate student. I was actually one of the first users of YT. And since then, it's been developed by a ton of people, and it's turned into this really amazing product for doing both analysis of lots of different kinds of simulations, not just astrophysics, but all sorts of other things, but also very sophisticated visualizations. So it's been lots of fun, but it's really important, so I wanted to mention it. Okay, so next up, why blue waters? I think you're getting a sense of why this kind of simulation might be expensive. But the things that I'm about to show you would be undoable on any other NSF or any other NASA resource that we could get our hands on. The simulations we're doing are a factor of 10, or well, actually, it's more like a factor of 100 times more sophisticated in terms of the volume simulated, the physics, the actual physical resolution than we could do anywhere else. And the reason why we can do it on blue waters, there's actually a few reasons. So first off, Blue Waters has a great interconnect. Very fast, very low latency. There's lots of memory per node. It gives us great scaling. And this combination of lots of memory and a very good interconnect really helps, especially for radiation transport, which is expensive and sort of algorithmically can be very challenging on supercomputers. Another thing that's really important about Blue Waters is the excellent file system. The I/O rates are great. It's very easy to create data, to write out a petabyte of data, and also to manipulate the simulation data later on when you're doing the analysis. That's what's really, really, really important. And also, we get rapid turnaround. So we're doing these simulations. They run on many, many processors, but also run for a tremendous amount of time, and in terms of wall clock hours. And so one of the really nice things about Blue Waters is that it's full of groups who know what they're doing, are running really big simulations. And so if you're running a really big simulation, the computer is tuned to help you out. And so it is very helpful for doing both the simulation, running the simulations, and analyzing the simulations. And again, the key point is that because of all of these great things, we can perform simulations on Blue Waters that are 10 to 100 times larger than possible on any of the Exceed systems, and certainly on NASA's Pleiades system. So so that it's a really unique resource for us for studying how galaxies form. Okay, so coming back to our big question, how the first galaxies form. What we're trying to compare to are these little things from that Hubble deep field. These are the most distant galaxies. The simulations look better, by the way. But these are the observations of the most distant galaxies. There aren't that many photons that the Hubble Space Telescope has captured from these. But these are at the point in time where we can compare to them with our simulations. And these simulations are unique in the sense that they have this radiation transport. Radiation from stars is very important. It affects galaxies. Galaxies affect their neighbors, particularly early on in the universe before everything is expanded. So they're all sort of bunched up right next to each other. Really phenomenal resolution, spatial resolution, also mass resolution. We can do things like form individual stars and look at the ionizing regions, what we call H2 regions, and the supernovae that come from these stars. And we're in the midst of figuring out how you get all these blobs. And so far, we've had lots of results. I'm not going to read all these to you, but these are the papers that either have already been published, are submitted to various journals, or will be submitted probably by the end of this month or next month sometime. So we've written 2, 4, 6, 7 papers so far, and the simulations are just a gold mine because they're so much bigger than anything that we've ever done before. We're just kids in a candy store at this point, looking through this and finding out all sorts of really cool stuff about galaxies. Okay, so there are 2 sets of simulations I want to tell you about. One of them is looking specifically at how the first generation of stars, which are primordial, they're made of just hydrogen and helium, none of the rest of the stuff on the periodic table, how those turn into metal-enriched stars. So as an astronomer, I like to refer to everything that's heavier than helium on the periodic table as a metal, which is reductive and angers chemists, and that's actually a really desirable outcome. But putting metal, all this other stuff heavier than helium, into a plasma means that it can cool much more efficiently. You can take your stars and go from really big hot stars and make more stars, take the same amount of gas, and it fragments and makes many more smaller stars, much more like our sun. And so it fundamentally changes the nature of star formation when you inject metals into the universe. And I'm doing that with Britton Smith, who's a former postdoc of mine. He's now at Edinburgh. John Wise, who's a professor at Georgia Tech, than me. And then we're also separately looking at the evolution of large numbers of early galaxies. This is with Hao Xu, who's a postdoc at UC San Diego, Pengfei Chen, who's a grad student, Mike Norman, who many of you know, and myself. And the people in yellow are the folks who really ran the simulations. So they're the ones who deserve much of the credit because they suffered the most. I just told them what to do. So, okay, so let's talk about this first set of simulations. So, a lot of text, we're going to blow right through this, but the point is that when you want to study how the universe goes from metal-free primordial stars to metal-enriched stars that are presumably much smaller, you pick a really small box because we only care about one or maybe a handful of halos. Then on top of that, you put lots of adaptive mesh. So 13 levels of AMR on the simulation, so it gives us really good, basically half a light year resolution. And then after the first star forms and the H2 region goes off and it explodes, we crank it up to 30 levels of refinement. So what we do is we just let the simulation refine wherever it wants because we want to understand how that first generation of metal-enriched stars forms. It has really phenomenal mass resolution and lots of physics. We'll skip past that. And then we're doing this in a paper which is going to be submitted next week if I ever will give Britton the draft back. So anyhow, so this is really cool stuff. So let's go to the movies because that's what we all want to see, right? So what we're looking at in this plot, it's going to be an evolution through time. So we're starting out about 10 million years after the Big Bang. In the top left field, we're looking at matter density. So this is where all the matter is. This is just a little piece of the simulation volume where the halos are forming. In the top right, this is the temperature. So you're going to see when the first star turns on and starts ionizing the universe, you're going to see the temperature get really hot. Down in the bottom left, that's the metals. All the metals are formed in stars at the end of their lifetimes. And so when the supernova blows up, when the star blows up, you see this big cloud of metals going out. And then down here on the right, this is molecular hydrogen, which is important as a cooling. And yeah, just ignore that one. So, okay, so let's go. So watch the density and the temperature, and then you're going to want to watch the metallicity. Okay, so the structures are collapsing. A star forms, you get this huge H2 region, and that hangs out for a couple million years, and then boom, you get a supernova down there. A second star goes off, H2 region, supernova. And then in that cloud, right here, that just slowly evolved for a little bit, is where our second generation star formed, really the first generation of metal-enriched stars. So what we're going to do now is take a deep dive down into this. And by the way, this was all done with YT, so we can, one of the nice things is it really helps if you want to do this kind of deep dive with this adaptive mesh refinement data. Okay, so we're going to just dive into that halo. So we're going over, I think, about 10 orders of magnitude here. The color tables have to keep changing to keep up. But basically, what you're seeing is us zooming in on this star-forming cloud. And you're seeing the gas is getting hotter, it's getting denser, and then right at the middle, the gas starts cooling like crazy, so it's gotten colder up in the top right-hand panel. And then you see a lot of sort of the gas, you see a lot of like a flocculent, like kind of cloudy, cirrusy structure up here in the top left in the gas. And that's because the gas, because the metals have been put into it, has fragmented like crazy. It's broken up into lots of little clumps that are probably all going to be their own stars, that are probably actually around the mass of the sun, our sun, which is a small and boring star. It's good to live around a small and boring star, by the way. And then you can see all the metals and how the metals are mixed together. And then you can see that the molecular hydrogen forms where the gas is dense. And so, but you really get a sense of what's going on when you dive in. And of course, we had this amazing resource available to us, so we didn't just do one of these, we did a bunch, and we played around with some different physics. And so this is when we looked at the effects of dust. So everybody knows what dust is, right? If you're as poor of a housekeeper as me, you have lots of it around. And it turns out that the universe is full of dust, right? It's not just under the kitchen table, right? And dust is is critical to a lot of things when it comes to forming stars, because dust is very good coolant. It's very effective at radiating away thermal energy and letting gas clouds collapse. It's also extremely effective at forming molecular hydrogen, which is another important coolant. And so if you put just a tiny, tiny amount of dust into your gas, it really changes the nature of things. And so over here on the right is a simulation where we didn't include the effects of dust, because there's a lot of debate in our field about whether these first generations of stars formed dust or not. We know that modern day stars form lots and lots of it, but there's reason to believe that these earliest stars don't. I can talk about that in the Q&A if you want. And so if they don't produce any dust, then what happens is what you see over here on the right. This is exactly the same simulation, where in one of them there's dust and the other is not. On the left it's dust, on the right it's not. On the top, we're looking at the gas cloud sort of zoomed out. On the bottom, we're showing it zoomed in. And so, no, I'm sorry. Top left is zoomed out a factor of 100 from the bottom left. Top right is zoomed out a factor of 10, and then we get to that. And then here we're looking at just the dust versus the no dust at the center part. Sorry about that. And so basically we see that this dust causes a lot more fragmentation. You get much smaller stars. And so what we've sort of done here is bracketed the two possibilities for this particular physical process. And that was great. That's great. That's very useful. We can go to incredibly high resolution, so we can state very definitively what's happening in this star-forming cloud. We can also do things like examine, as a function of the density of the gas. So from left to right, the gas is getting more dense. From bottom to top, there's more molecular hydrogen. The red line is the dust. It's actually a distribution. And the blue line is not. And you can see that the dust, this line with the dust, there's way more molecular hydrogen. So it's a factor of 10 more. This is a log-log plot. And so that really affects the structure. And that's all I'm going to say about this. I was maybe a little reluctant to show too many plots, but we're writing a paper and it's very exciting, and we can talk more about that later. Okay, so those are the first simulations that we did, and then we've also worked on these really, truly enormous calculations where we're studying early populations of galaxies. And these simulations are remarkable. They cost, depending on the calculation, between sort of 20 to 35 million core hours. So divide by 16 to get node hours. But what we did was we wanted to understand how different regions of the universe evolve. Because we know nowadays there are really dense regions of the universe that are those galaxy clusters that I showed you. There's very low density regions of the universe, which are voids, which are essentially empty. And then there's things that are more average, which is where you get galaxies like the Milky Way. And so there is reason to believe that this extends all the way back to shortly after the Big Bang, where the differences wouldn't be so stark, but 500 million years after the Big Bang, some of the universe is going to be a factor of 2 or 3 denser than other pieces of the universe, on sort of large scales. And so we wanted to look at how a dense region of the universe evolved, an average density region, and a low density region evolved, because there's reason to expect that the galaxies in those regions might evolve differently. And so what we did was run a simulation, a sort of a simple simulation, and find these regions, and then go back and refine the heck out of them. So use really fantastic mass resolution and spatial resolution, and again, radiation transport and prescriptions for star formation and feedback and all the stuff that I was just talking about, and follow the evolution of this. And we've been mining these simulations for data, and we've written a ton of papers so far, and there are many more to come. Okay, so let's show some pictures. And I should say, before I show you what I'm about to show you, we've been busy writing journal articles, and we haven't spent a lot of time doing visualization yet. One of the reasons I'm here this week is to hit some folks up locally to help me with that. But basically, this is what a huge region of the universe that's full of about 1,000 galaxies at 500 million years after the Big Bang looks like. So that's 4% the age of the universe. This is we're looking at a projection of matter density. So all of those red and yellow regions are full of galaxies, 1,000 of them. And for the purposes of comparison, prior to this, the best simulations that have been done with this kind of physics had maybe 8 galaxies in them. So 125 times better. Suddenly we're talking about statistics here, like really useful stuff and not just anecdote. And so, shots fired. Anyway, so this is the density field. Okay, so I talk a lot about radiation transport. What do you see with radiation transport? This is what you see. So this is a plot of the temperature field. And let me just toggle back and forth. So look at where the matter is in these little filaments, and the temperature field is producing, so what is happening here? The stars that are forming are producing a lot of radiation, ultraviolet radiation, and it ionizes all the gas around it. It puts lots of energy into that gas, makes the gas very, very hot. But because the universe is smaller and more compact than it is today, factor of 15, 20 times smaller, so a factor of thousands more dense, the ionizing radiation can't go very far. So those galaxies are surrounded by these little bubbles of ionizing radiation, and they actually interfere with with other galaxies. So around the outskirts of this big sort of region of galaxies, you see little isolated bubbles of hot gas, which is isolated bubbles of radiation. Near the center of it, you see much less isolation. The galaxies are all closer together, they're all forming stars like crazy, and they're starting to share these big ionized regions. And so what's happening to the galaxies on the outskirts of this region is very different than what's happening to the galaxies that are inside of this region. And we expect that if we carried out this simulation for another 500 million years, we would see that the whole volume would essentially become completely ionized and be completely filled with ultraviolet radiation. But this period in the middle, while it's happening, is really fascinating because the nature of galaxy formation is completely changing right here. And also, all of these stars are dying. They live for a while and then they explode. And when they explode, they make supernovae and they fill the universe with metals. And we've already talked about why metals are important. And then we get these bubbles of metal all over the place. And they're not as widely distributed as the radiation. They follow the galaxies much more closely. This is very abstract, I appreciate that. But we can find out all sorts of good stuff from looking at that. How much more time do I have?
A few.
Wrap it up?
Yeah.
Aye, aye. Message received. Okay, so we're going to skip the rest of the results, of which there are many and I'd be happy to tell you about. But let me tell you something that I think is very important and I want to discuss. So the NSF has invested a lot of resources into blue waters, and it's invested a lot of those resources into doing the astrophysical research that we are doing. And quite frankly, we have produced a petabyte of data, and there are so many interesting pieces of science that one could explore with this that what we want to do, the whole collaboration that's been working on these simulations, is we want to give it away. We want to give it to the community because there are lots of other people. They also have good ideas. We want to give them our simulation data. And they can go download YT off the internet, and they can analyze this data and hopefully produce lots of good science and can leverage, leverage what we've done so that we can learn way, way more about galaxies. And we've actually, I've spent a lot of time this week talking to people about exactly how we can share this data and how we can most effectively share this data. Because really, I mean, these things were expensive and they should be a community resource and they should, be useful for many, many years. So we really want to just share it so people can leverage it. Okay, so what do I want you to take away from this talk? First off, modeling galaxy formation is complicated. It's physically complex, and it requires a very high dynamic range and a big sample size. You need lots of galaxies to sort of statistically understand what's going on, and all the physics and spatial issues that I was talking about. And so that is a computationally challenging task, which drives us to ask for lots of time on machines like blue waters. Very special machines that have really critical properties for us to do this work. So, because we have blue waters, we are using it to performing these really cutting-edge simulations. And we're looking at the first generations of stars and the first generation of galaxies. And these are simulations that are 1 to 2 orders of magnitude bigger than you could do absolutely anywhere else in the NSF or NASA, sort of computational infrastructure. And what we're finding from the simulations, which I showed you a little of, but we didn't really get too much into, is that the transition between this metal-free star formation and metal-rich star formation is, very complex. It also lasts a long time. And there's all sorts of really fascinating physical effects that are going on. And then we didn't actually get to this last one, but we find one of the really interesting results that we find is that the lowest mass galaxies in these simulations are really easy to stop from forming stars. And so it will really affect what the Hubble Space Telescope sees and also what the James Webb Space Telescope sees when it gets launched in a few years. So we've made some very cool predictions. So thank you very much for giving me this opportunity. And let me just go ahead and put that back up again.
All right. Thanks, Brian. So I think we have a few moments for a couple quick questions before we head out into the atrium area. Or if you have some follow-up questions, you can always meet Brian outside. So any quick questions? Oh.
You're either impressed or baffled.
I just wanted to ask if you use your simulations and data as part of any teaching activities.
Will we use the simulations?
Or are you? I mean, do you use
yes.
simulations when you're...
Absolutely. Well, so we've studied the first 500-600 million years of evolution, and it brings a big set of questions. And one of the questions that I think is really critical is how can we best tie these early generations of galaxies to the Milky Way? And that's a critical research question because these galaxies, when you observe those galaxies, they're very far away. They're billions of light years away. So they're very dim and they're hard to see and you only see the brightest ones. The Milky Way, on the other hand, we're sitting smack dab in the middle of it. And we know from the things that I showed you that structure forms hierarchically. So little galaxies merge together and make bigger galaxies and so on and so forth. And so in other words, those galaxies that we've been simulating, and this is one of the supernova remnants from Britain's simulation, one of these galaxies, or millions of these galaxies maybe, well, no, it's more like tens of thousands of these galaxies. Sorry, didn't mean to backpedal so vigorously there. Many of these galaxies merge together to form the Milky Way and the satellite galaxies that are around the Milky Way and things that are local that we can actually study. And so the trick is making the connection between the galaxies that we've been simulating and the Milky Way. And as a matter of fact, I was just very recently awarded a Great Lakes Consortium grant to take the data that we're using right now and turn it into simulations that will form the Milky Way down the road. So it's directly informing the next step of research that we're taking with this work.
You showed that you use some Sloan data. Are you planning to use the data that comes from the dark energy survey or from LSST?
There's no possible reason why you'd be asking me that, is there? Well, this actually comes back to Gabrielle's question. Dark energy survey and LSST are mostly going to be focused on galaxies that are closer than what you see, than those really distant ones in the Hubble Ultra Deep Field. However, LSST and the Dark Energy Survey are looking out through the Milky Way galaxy. And they're phenomenal surveys in terms of their photometry, the color coverage, things like that. And so as a result, you can use those surveys to find out a ton about the Milky Way itself and its stellar population. So you can use the Dark Energy Survey, for example, to find new dwarf galaxies. And there was just a paper published earlier this week where they found nine new dwarf galaxies using the existing DES data. And so that informs the simulations that we plan to do, and it will inform how we interpret the results. And also, so I'm a member of the LSST Galaxy Science Collaboration, and so we hope to turn that around and make predictions about the galaxies, particularly local galaxies, the little, small, dim local galaxies that LSST might see down the road. Because they're very hard to find. I mean, they're very dim, they're very small. There's an awful lot of Milky Way stars between the telescope and these dwarf galaxies. And so you have to be very, very clever to pull out the dwarf galaxies and all of this other structure from the foreground stars. And so one of the things that we ought to be able to do as we use our simulations and also spend a lot of time working with YT to build synthetic observing tools so we can actually make things that look like they come out of the LSST, to come up with ways to more effectively find things like these really old, tiny, dead dwarf galaxies that are really relics from the era that I'm showing you here, or that I've been talking about in this talk. So yeah, so it actually directly connects, and I'm very excited about LSST in particular, but DES is going to be very important as well. So.
Right, one more quick question.
Multi-scale, multi-physics, great way to get things done. What other domains would benefit from your techniques?
Right. Well, so multi-scale, multi-physics is a nice way of putting it, right? So we have lots of different things, lots of different types of physics that are interacting over a wide variety of scales. This can couple different scales together. Sometimes you have to be very clever about how you simulate these different things because the techniques you use to simulate the hydrodynamics versus the chemistry versus the radiation transport are quite different. Look, it's physics. Radiation is a thing. Radiation is everywhere. Fluids are everywhere. The problems that we are dealing with are very similar to the problems that someone who wants to model, well, let's just say you had a high altitude airplane, and you're interested in how the air flows around the wing. It's the same problem. There's lots of scales. There can also be chemistry going on. Maybe the gas is dense enough that it doesn't quite act like atmosphere at sea level, so you have to deal with sort of plasma effects. The problems are very similar. And so, as a matter of fact, you teed this one up for me, we all know, but we've been working with collaborations of people in industry and in other scientific disciplines because this is very common. You have big things where a small piece of it is interesting or a small piece of it is important, and you have lots of physical effects that are going on at the same time. An automobile engine is a perfect example. I don't know, I always go back to planes because I like planes, but there's plenty of examples, and the techniques you develop to do these adaptive mesh, things like adaptive mesh, coupling together chemistry and hydrodynamics and radiation and all that stuff, is discipline agnostic because fluids are fluids and radiation is radiation, and both of those things are everywhere. And so a lot of the techniques directly transfer. So, I mean, the scales are wildly different, of course. The physical scales are wildly different, of course, but the technical challenges are pretty much identical.
All right, I think if you have any more questions, I think you can hold them and talk to Brian outside. So let's thank the speaker one more time.